Okay, let's get into it. Number 11. Dark matter might not exist. Here's a fact that should bother you more than it does. When we add up everything we can see in the universe, every star, every glowing cloud of gas, every planet and moon and speck of dust, we get about 15% of the matter that has to be there. The other 85% is invisible. We can't see it. We can't touch it. We've never caught a single particle of it in any detector on Earth. We call it dark matter, and we're pretty sure it's real because galaxies spin far too fast to hold themselves together without it. Without extra gravity, a spiral galaxy rotating at the speeds we measure should have flung its outer stars into deep space billions of years ago. So the universe is mostly made of something we've never found. That's the official story. But in 1983, an Israeli physicist named Mordechai Milgram looked at the same problem and asked a heretical question. What if there's no missing matter at all? What if we're not missing anything, and the thing that's actually broken is our law of gravity? His idea is called modified Newtonian dynamics, or MOND, and it's beautifully simple. Milgram proposed that when gravity gets extremely weak, weaker than about 1 part in 10 billion of what you feel standing on the ground, it stops following Newton's neat inverse square law and starts falling off more slowly. Out at the faint edges of a galaxy, that tiny tweak is exactly enough to keep the stars in their orbits. No invisible halo required. And here's the thing. It works. It works embarrassingly well. Milgram's formula predicts the rotation of hundreds of galaxies, from giant spirals down to faint dwarfs, often more accurately than dark matter models do. And it does it with a single number instead of a custom-fitted cloud of invisible stuff for every galaxy. There's a relationship called the Tully-Fisher law, connecting how bright a galaxy is to how fast it spins, and MOND predicts it naturally. Dark matter has to be tuned to reproduce it. You would think a theory that keeps getting galaxies right would be celebrated. Instead, it's the idea you're warned not to take too seriously. Because MOND has a weakness, and it's a big one. Zoom out from a single galaxy to a whole cluster of galaxies, and MOND stops being enough. It still needs some unseen mass to make the numbers work. And it has no clean story for the afterglow of the Big Bang, or for the bullet cluster, that famous cosmic collision where the gravity and the visible matter appear to have separated, which most physicists read as a smoking gun for real dark matter. So the mainstream keeps its invisible 85%, and MOND sits in the corner, too successful to dismiss, too incomplete to crown. But every time someone measures a new galaxy and it falls exactly on Milgram's line, a few physicists feel a quiet chill. Because either the universe is overwhelmingly made of a substance we cannot find, or the force that shapes everything is not quite the force we think it is. Neither answer is comfortable, and the galaxies aren't telling us which one is true. Number 10. The speed of light was not always the same. There are a few numbers in physics that feel less like measurements and more like commandments. The speed of light is the first among them. 300,000 kilometers per second. Nothing goes faster. It's woven into Einstein's relativity, into E equals mc squared, into the very structure of cause and effect. Question it, and you're not doing physics anymore. You're doing science fiction. Unless you're Juan Magejo. In 1998, Magejo, working with Andreas Albrecht, proposed something that got him treated like a heretic in his own field. He suggested that in the first sliver of a second after the Big Bang, light didn't travel at the speed it does now. It traveled much, much faster. Perhaps 30 orders of magnitude faster. A 1 with 30 zeros after it. Now, why would anyone propose something so reckless? Because of a genuine puzzle called the horizon problem. When we look at the afterglow of the Big Bang, the cosmic microwave background, it has almost exactly the same temperature in every direction, to a startling precision. But regions on opposite sides of the sky are so far apart that, in the age of the universe, light has never had time to travel between them. They've never been in contact. So how did they agree on a temperature? How do two rooms that have never exchanged a whisper end up at exactly the same warmth? The mainstream answer is cosmic inflation, the idea that the infant universe ballooned faster than light for a fleeting instant, stretching one tiny uniform patch across the whole sky. It's elegant, it's popular, and it works. Magejo's answer was different, and, frankly, more insolent. Don't inflate space, he said. Just let light be faster. If light moved fast enough in the beginning, those distant regions could have exchanged heat after all, settled into the same temperature, and then light slowed to the sluggish crawl we measure today. The reason this matters, the reason it isn't just idle provocation, is that Magejo's theory makes a prediction. A varying speed of light and standard inflation leaves slightly different fingerprints in that cosmic afterglow. Magejo's model points to a specific value for how the ripples are distributed across scales, a number around 0.965, which means one day, with precise enough measurements, we could actually catch one of these theories being wrong. That's the part that unsettles people. This isn't unfalsifiable mysticism. It's a rival that agrees to be tested. And if it ever wins, the most sacred constant in physics becomes just another quantity that used to be something else. The commandment turns out to be a suggestion. For now, inflation holds the crown. But somewhere in the fine grain of the oldest light in existence, there's an answer to whether the speed of light has always been what it is. We just aren't quite able to read it yet. Number 9. White holes. Everyone knows what a black hole does. It swallows light, matter, time itself. Anything that falls past the edge is gone forever, dragged down to a point where our physics stops making sense. It is the ultimate one-way door. Now, run the film backwards. A region of space that nothing can enter. A place that only ever expels, never absorbs. Matter and light come pouring out of it, and no matter how hard you try, you can never cross the boundary to get in. That's a white hole. And here's the strange part. It isn't a fantasy someone invented for a story. The same equations of general relativity that give us black holes also permit white holes, cleanly, mathematically, as the time-reversed mirror image. Einstein's mathematics says they can exist. Nature just doesn't seem to have made any. Or has it? Enter Carlo Rovelli, one of the leading minds in quantum gravity, who took this discarded curiosity and built something audacious on top of it. Rovelli asked what really happens at the very end of a black hole's life. Black holes aren't eternal. They slowly leak energy through a process called Hawking radiation, shrinking over unimaginable spans of time. The standard picture says a black hole just evaporates down to nothing and vanishes. But Rovelli argues that when it shrinks all the way to the Planck scale, the smallest meaningful size in physics, quantum effects slam the brakes. The collapse can't continue. And so, the black hole flips. It undergoes a quantum bounce and becomes a white hole, a tiny one. Planck-sized on the outside, but with a vast interior, like a cathedral folded into a grain of sand. And then Rovelli, working with Francesca Vidotto, took one more step, the step that makes this genuinely dangerous. What if the universe is full of these remnants? Countless tiny white holes, left over from black holes that finished evaporating, drifting invisibly through space. They would have mass. They wouldn't shine. They wouldn't interact with light. Which is to say, they would look exactly like dark matter. Sit with that for a moment. The invisible scaffolding holding every galaxy together, the mysterious 85% from a few minutes ago, might be the tombstones of dead black holes. Not new particles. Not exotic forces. just the quiet, burned-out remains of the most violent objects the universe has ever made. Ravelli points out this is a dark matter candidate that needs no new particles, no new forces, nothing beyond the physics we already have, taken seriously enough. Of course, no one has ever seen a white hole. They may be unstable. They may be impossible to form in practice. The whole idea sits on the far edge of speculation. But every black hole out there is, by this reasoning, a white hole waiting to happen. Slowly, patiently, over spans of time that dwarf the current age of the cosmos, one door may be turning into its opposite. The thing that only ever takes may be destined to become the thing that only ever gives. Number 8. There was no Big Bang, only a bounce. We tell the story so confidently now. 13.8 billion years ago. Everything, all of space, all of time, all of matter and energy, was compressed into a single point of infinite density. The Big Bang. Time began. Before it, there was no before, because there was no time for a before to happen in. It's a beautiful story. It's also, quietly, an admission of failure. That single point of infinite density has a technical name. It's called a singularity. And a singularity is not a triumphant beginning. It's the place where our equations break. Densities go to infinity. Curvatures go to infinity. And general relativity throws up its hands and stops giving answers. When a physicist says the universe began in a singularity, what they're really saying is, we have no idea what happened, and our best theory refuses to tell us. So a group of physicists decided to fix the theory instead of worshiping the mystery. Their tool is called loop quantum cosmology, and it comes from the effort to weld quantum mechanics onto gravity. In the early 2000s, Martin Bojewald and others found something remarkable when they applied it to the birth of the universe. The singularity disappears. In its place, something extraordinary happens. As you rewind the universe toward that first instant and the density climbs toward the Planck scale, gravity does something it never does in everyday life. It reverses. It becomes repulsive. That crushing inward pull that builds stars and black holes flips into an outward push, powerful enough to stop the collapse and throw everything back out again. They call it the Big Bounce. And the implication is staggering. In this picture, our universe did not begin. It rebounded. Before our expansion, there was a previous universe, an older cosmos, contracting, falling inward under its own gravity, growing denser and hotter until it reached that unbearable limit and bounced, blossoming outward into everything we now call home. What we named the beginning of time was really a moment of transition, a door between one universe and the next, which means time might have no beginning at all. The question, what came before the Big Bang, stops being forbidden and starts being answerable. What came before was another universe, living out its own long history, unaware that its death would be our birth. Now, is any of this proven? No. Loop quantum cosmology is still a work in progress, built on a theory of quantum gravity that itself remains unconfirmed. We have no photograph of the universe that came before, no message left in the rubble. The bounce lives in the mathematics, not yet in the data. But it changes the shape of the question. For a century, we've treated the beginning as a wall, a place where curiosity has to stop. The bounce suggests there is no wall, just a threshold, and a darkness on the other side of it that used to be a universe. Maybe the cosmos doesn't begin and end. Maybe it just breathes. Number 7. Dark energy might be an illusion. In 1998, astronomers made a discovery that won a Nobel Prize and broke everyone's brain a little. The expansion of the universe isn't slowing down, as gravity should demand. It's speeding up. Something is pushing the cosmos apart, harder and harder, and we have no idea what it is. We gave it a name that's really just a confession of ignorance dressed up as knowledge. Dark energy. It supposedly makes up about 70% of everything, and it is the single largest mystery in physics, unless it isn't there at all. This is the claim of David Wiltshire, a cosmologist at the University of Canterbury in New Zealand, and it's the kind of idea that makes established physicists deeply uncomfortable, because if he's right, we didn't discover a new force. We made a mistake. Here's the heart of it. When we do our standard cosmology, we make a simplifying assumption. We pretend the universe is smooth, that matter is spread out evenly, like fog. But the real universe is nothing like that. It's lumpy, ferociously lumpy. Galaxies cluster along enormous filaments and walls, and between them yawn vast, nearly empty voids, hundreds of millions of light years across. And here's the detail that most people never learn. According to general relativity, time itself runs at different rates in these different regions. In the empty voids, where gravity is weak, clocks tick faster. In the dense walls where galaxies huddle, clocks run slower. Wiltshire's timescape model says that when you properly account for this, for the fact that the universe is a patchwork of fast and slow clocks and fast and slow expansion, the illusion of acceleration appears on its own. We're not seeing a mysterious force pushing everything apart. We're seeing the honest consequence of a lumpy universe, misread by a theory that assumed it was smooth. Dark energy dissolves, not defeated by a new discovery, but revealed as a bookkeeping error on a cosmic scale. For years, this was easy to wave away. But then, in December of 2024, Wiltshire's team, working with the group behind one of the best supernova datasets in the world, reanalyzed 1,535 exploding stars, and their result landed like a stone through a window. On that data, the timescape model didn't just survive. It competed with the standard model of cosmology, and by some measures, it fit better. Let me be honest about where this stands. Most cosmologists are not convinced. The statistical edge is real, but modest, and the assumption that the universe is smooth on the largest scales has served us extraordinarily well. Dark energy is still the mainstream answer, by a wide margin. But imagine, just imagine, that it holds. That the greatest mystery in modern physics, the 70% of the universe we've been chasing for a generation, was never a substance or a force, just a shadow cast by our own arithmetic. Sometimes the monster under the bed turns out to be a coat on a chair. The unsettling part is how long we were afraid of it. Number 6. Dark energy might be dying. Suppose, for a moment, that we set the last idea aside. Suppose dark energy is real. 70% of the universe, a genuine force pushing the cosmos apart. For decades, we assumed that if it's real, it must be constant, unchanging. A fixed property of empty space itself, the same yesterday, today, and 100 billion years from now. Einstein even had a name for it, tucked into his equations. The cosmological constant. The very word constant is baked into how we think about it. And now the data is whispering that the constant might not be constant at all. The whisper comes from an instrument called DESI, the Dark Energy Spectroscopic Instrument, sitting on a mountaintop in Arizona. DESI is building the largest three-dimensional map of the universe ever made, capturing light from tens of millions of galaxies and quasars, using them like buoys to measure how fast the cosmos has expanded at different points in its history. It is, in effect, a time machine, letting us watch dark energy do its work across billions of years. And in 2025, DESI's second data release delivered a genuine shock. When you combine its map with the afterglow of the Big Bang, with distant supernovae, with the way gravity bends light across the sky, a pattern emerges. Dark energy does not look constant. It looks like it's weakening, fading. It appears to have been stronger in the past, and to be losing its grip as time goes on. The strength of the signal reached about 4.2 sigma. In plain terms, that's roughly a 99.9 95% chance it isn't a fluke. Not quite the gold standard physicists demand, before they'll truly celebrate. That's 5 sigma, but close enough that the whole field sat up straight. And think about what a dying dark energy would mean. For years, the assumed fate of the universe was a cold, lonely stretching called the Big Freeze, or if dark energy grew strong enough, a violent tearing apart called the Big Rip. Both assume dark energy stays or strengthens, but if it's fading, all of those endings are back on the table, and new ones open up. Maybe the expansion slows. Maybe, in the deep future, it even reverses. The ending of the universe, the actual final chapter of everything, is being rewritten right now, in data coming off a telescope while you sit here watching this. I want to be careful. 4.2 sigma is not certainty. The signal leans on combining several data sets, and some researchers suspect a subtle error in how we calibrate distant supernovae could be masquerading as evolution. It might yet evaporate, but it might not. And if it holds, Einstein's constant, the thing we named for its permanence, will turn out to have been changing under our noses the entire time. The universe kept a secret in plain sight, written across billions of galaxies, waiting for us to build an eye sharp enough to read it. We just built the eye. Now, we're learning to read. Number 5. Reality might be a hologram. I want you to look at your hand. Feel how solid it is, how it takes up space, how it has depth and volume and mass. Now consider the possibility that all of that, the three-dimensional richness of everything you have ever experienced, is a kind of projection. That the real action, the actual information that makes up you and this room and the entire universe, is stored on a distant two-dimensional surface, and what you're living inside is the image it casts. This is the holographic principle, and the reason you can't dismiss it as stoner philosophy is that it came out of the hardest, most respected physics there is. It began with a paradox about black holes. In the 1970s, physicists realized black holes have entropy, a measure of how much information they contain. But here's the shock. A black hole's information doesn't scale with its volume, the way you'd expect for anything three-dimensional. It scales with its surface area. The amount of stuff you can cram into a black hole is written on its boundary, not throughout its interior. That's bizarre. It's as if the contents of a warehouse were fully determined by the paint on its walls. In 1993, the Nobel laureate Gerard 't Hooft took this seriously and made a radical leap. If a black hole stores its information on its two-dimensional surface, maybe everything does. Maybe any region of space can be completely described by information living on its boundary. Leonard Susskind sharpened the idea a year later in a paper with a title that says it all, The World as a Hologram. And then, in 1997, this stopped being a hunch and became mathematics. Juan Maldacena discovered a precise, calculable relationship, now one of the most cited results in all of theoretical physics, showing that a universe with gravity in a certain kind of space is exactly equivalent to a universe with no gravity at all, living on its lower dimensional boundary. 2 descriptions, one with an extra dimension and one without, describing the identical reality. The gravity, the depth, the third dimension, all of it can be reconstructed from information painted on a flat edge. Now, the honest caveat. Maldacena's exact result works in a type of space that is not quite our universe. Our cosmos isn't shaped the way his mathematics requires, so we can't yet claim, with proof, that our reality is a hologram. It's a principle that works beautifully in a nearby idealized world, and physicists are still fighting to extend it to ours. But the mere fact that it works at all should stop you cold. It means the number of dimensions you experience might not be fundamental. It might be emergent, a convenience, a way of organizing information that could equally well be arranged with one less dimension. The depth you feel, the space you move through, could be the universe's way of telling a two-dimensional story in three-dimensional language. you are not losing anything if it's true. The hologram is just as real as anything else. But the stage might be flatter than it looks. And somewhere out at the edge, in a place you can never visit, the whole play might be written on a single surface, thin as a thought. Number 4. The universe before ours. Roger Penrose is not a crank. Let's establish that first. He shared a Nobel Prize for proving, with Stephen Hawking, that general relativity demands singularities at the hearts of black holes. He is one of the most decorated mathematical physicists alive. So when a man like that stands up and says he can see the fingerprints of a universe that existed before our own, printed across our sky, you don't laugh. You lean in. Penrose's theory is called conformal cyclic cosmology, and to understand it, you have to think about the very far future. Fast forward past the death of every star, past the slow evaporation of every black hole, past the last flicker of any organized structure. In something like a Google years, the universe becomes an almost perfectly smooth, cold, empty expanse. Nothing but faint radiation, spread thin across an unimaginable void. No matter, no clocks, nothing to measure size or time with at all. And here Penrose makes his strange, brilliant leap. He argues that a universe with nothing in it to measure scale becomes mathematically indistinguishable from a universe that is infinitely small and dense. The cold, endless end and the hot, tiny beginning become the same thing. And so, the dead, empty, far future of our universe becomes the Big Bang of the next one. The end is the beginning. Not metaphorically, geometrically. Aeon after aeon, universe after universe, each one's death igniting the next one's birth. It's a gorgeous idea, but Penrose did something a philosopher wouldn't. He asked whether it leaves evidence, and he thinks it does. In the previous aeon, giant black holes would have spent eons swallowing everything around them, and then slowly evaporating away through Hawking radiation, dumping enormous quantities of energy into their universe over vast stretches of time. Penrose argues that when one aeon passes into the next, those bursts of energy get concentrated and carried across the boundary, leaving faint circular marks in the afterglow of our own Big Bang. Warm rings in the cosmic microwave background. He calls them Hawking points. Scars from black holes that died in a universe before ours. In 2020, Penrose and his colleagues published a paper claiming they'd found them. Anomalous warm spots in the sky, exactly where the theory said the corpses of a previous cosmos should be glowing through. Now, I have to be fair, and the fairness cuts hard here. Other teams reanalyzed the same data with more careful statistics and found nothing. When you properly account for random bright and dark patches, they say, the Hawking points vanish into noise. Most cosmologists remain unconvinced, and inflation is still the standard story of our beginning. But I can't quite shake it, because if Penrose is right, then, on a clear night, when you look up at the faint hiss of the cosmic microwave background, the oldest light there is, you are not just looking at the dawn of everything. You are looking at the ashes of an older world, still faintly warm, bleeding its last light into ours. We may not be the first, we may just be the latest. Number 3, universes that breed through black holes. Here is a question that keeps cosmologists awake, and it's simpler than it sounds. Why are the laws of physics the way they are? The strength of gravity, the mass of an electron, the force that binds atomic nuclei, dozens of these fundamental numbers, and every single one of them sits in a narrow window that allows stars to burn, chemistry to happen, and life to exist. Nudge almost any of them a little, and you get a dead universe. No stars, no atoms, nothing. The usual explanations are unsatisfying. Either it's blind luck, which feels absurd given how many numbers had to line up, Or there's a designer, which is not science. Or there's a vast multiverse, and we simply live in one of the rare universes that works, which explains everything and predicts nothing. Lee Smolin, a physicist never afraid to provoke his own field, offered a fourth answer in 1992, and it is genuinely one of the most creative ideas in modern cosmology. He asked, what if universes evolve? What if they reproduce and mutate and are selected exactly like living things? Here's how it works. Smolin proposes that every black hole, at its core, gives birth to a new universe. The collapse that forms a singularity on our side becomes a Big Bang on the other side, budding off a whole new cosmos we can never see. And crucially, when a baby universe is born this way, it inherits the laws of its parent, but with slight random changes. Small mutations in the fundamental constants. Now follow the logic, because it's ruthless and beautiful. A universe with constants that happen to produce lots of black holes will have lots of babies. A universe with constants that produce few black holes will have few. So over countless generations of universes, the population comes to be dominated by cosmoses that are extraordinarily good at making black holes. It's natural selection, but the trait being selected isn't survival or speed. It's fertility. The ability to make black holes. And here's the payoff that makes this science instead of poetry. Black holes are made from collapsing giant stars. The same conditions that make lots of black holes, plenty of carbon, stars of the right size, stable chemistry, are remarkably close to the conditions that allow life. We might not be fine-tuned for us at all. We might be a side effect of a universe fine-tuned by generations of cosmic evolution to make black holes. Our existence would be an accident riding along on the universe's real talent. Best of all, Smolin did something almost no multiverse theorist dares to do. He made it falsifiable. His theory predicts that our universe's constants should be nearly optimal for producing black holes. Find a simple change to the laws of physics that would make more black holes, and the theory is dead. That's a real, testable bet, and critics have been swinging at it for years, arguing that certain tweaks would indeed make more black holes. But whether it survives or falls, sit for a moment with the vision. A cosmic lineage stretching back through countless parent universes. Physical laws not decreed, but evolved. And every black hole in our sky, every one of those dark, silent mouths, potentially a womb, quietly giving birth to a universe of its own. We may not be creations, we may be descendants. Number 2, the entire universe might be spinning. Almost everything in the cosmos turns. The Earth spins on its axis. The moon circles the Earth. The planets wheel around the sun. The sun itself sweeps around the center of the Milky Way, a galaxy that is one enormous rotation. Spin is everywhere you look, from a figure skater to a hurricane to a galaxy 100,000 light years wide. So here's a question so simple it feels childish, and so profound it borders on forbidden. If everything in the universe rotates, does the universe itself rotate? For a century, the answer from cosmology has been a firm no. One of the foundational assumptions of modern cosmology is that the universe has no preferred direction. Look any way you like, and on the largest scales it should appear the same. No axis, no spin. A universe that rotated would have a special direction, an axis threaded through all of creation, and that idea has been quietly considered almost taboo. But in 2025, a team of physicists, led by Istvan Saputty at the University of Hawaii, revived it, and they did it for a very practical reason. They were trying to solve the single most stubborn crisis in cosmology, a crack in our understanding so persistent it has its own name. The Hubble tension. The tension is this. When we measure how fast the universe is expanding by looking at the nearby cosmos, we get one number. When we measure the same expansion rate from the afterglow of the Big Bang, the distant early universe, we get a different number. And these two measurements, both done with exquisite care by brilliant people, stubbornly refuse to agree. Something is wrong, either with our measurements or with our understanding of the universe itself, and nobody has been able to fix it. So Saputi's team asked, what if we let the universe rotate? Just a little. They built a model inspired by a famous solution Kurt Gödel found back in 1949, when Gödel showed that Einstein's equations mathematically permit a rotating universe. Gödel's original version was wild, allowing loops in time where you could travel into your own past. Saputi's team built a tamer cousin, a universe with a gentle, almost imperceptible spin, without the time travel madness. And here's the astonishing part. The rotation they needed was fantastically slow. About one turn every 500 billion years. That is so slow it's effectively undetectable, far slower than anything we could ever hope to measure directly. And yet, in their model, that whisper of a spin is enough to reconcile the two clashing measurements of cosmic expansion. The crack in cosmology closes. Think about what that would mean. Not that the universe is a spinning top, nothing so dramatic, just that the entire cosmos, everything that exists, everything you have ever seen or will ever see, turns once so slowly that in the whole history of the universe so far, it hasn't even completed a fraction of a single rotation. A spin you could never feel, threaded through an axis you could never find, quietly shaping the expansion of all of reality. It's a single unconfirmed model, and cosmic uniformity remains very well supported. This may be wrong, but if it's right, then the universe has been turning all along, patiently, invisibly, and we've been riding it without ever once feeling the motion. Number 1. You might be one of infinite copies. 1. We've saved the vastest idea for last, and I want to build it slowly, because it starts from solid ground and ends somewhere that will make the floor feel unsteady beneath you. Start with inflation, the leading theory of how the universe began. In the first unimaginably tiny fraction of a second, space expanded faster than light, doubling and doubling, smoothing the cosmos into the uniform expanse we see. That much is close to mainstream. But in the 1980s, Alan Guth, Andrei Linde, and Alexander Vilenkin followed the logic further, and what they found was almost impossible to accept. Inflation, once it starts, doesn't fully stop. Here's why. Inflation is driven by a strange high-energy field, and that field decays randomly in fits and starts, quantum mechanically. In some regions it decays, inflation ends, and a calm universe like ours settles out, a bubble of normal space. But in the space between those bubbles, inflation keeps going, expanding so ferociously that it creates far more space than the bubbles consume. So new bubbles keep forming, forever, in a background that never stops inflating. They called it eternal inflation. Once it begins, it makes universes without end. Each bubble is a complete universe. And here's the vertiginous part. There's no reason for these other bubbles to have the same laws as ours. Different strengths of forces, different particles, different physical constants, perhaps different numbers of dimensions. An endless, frothing multiverse of universes, each one a separate experiment in how reality could be arranged, and ours just one bubble among an infinity of others. Now take the final step, the one that reaches out and touches you personally. If the multiverse is truly infinite, and matter can only be arranged in a finite number of ways within any given region, then arrangements have to repeat. Everything that can happen does happen, not once, but infinitely many times, which means somewhere out there is another Earth, another version of this exact moment, another you, sitting exactly where you are, watching exactly this, right down to the last thought passing through your mind. And not just one, infinitely many. Some identical, some where you made one different choice, some where you never existed at all, and now the part that keeps physicists up at night. Those other bubbles are, by the very nature of the theory, unreachable. The space between them inflates faster than light, so we can never travel to them, never see them, never receive a single photon from them. They are cut off from us absolutely and forever, which means this grandest of all ideas may be permanently untestable. Not hard to test. Impossible. That's what makes it so dangerous. Some physicists embrace it as the natural consequence of our best theories. Others recoil. Paul Steinhardt, who helped build inflation in the first place, turned against this conclusion, calling the multiverse, and I quote, baroque, unnatural, untestable, and in the end, dangerous to science and society. When one of the architects calls his own creation dangerous, you know you've reached the edge of what science can hold, and maybe that's the right place to end. Because every theory we've walked through tonight lives in that same trembling zone, right at the border between the knowable and the forever hidden. Dark matter that might be a mistake. A speed of light that might have changed. A universe that might have bounced, might be spinning, might be a hologram, might be one of countless children budding off black holes. These aren't the fantasies of cranks. They're the honest, uncomfortable frontier of people who take the mathematics seriously and follow it past the point of comfort. We like to imagine science as a finished map with a few blank corners left to fill in. It isn't. It's a small circle of light in an enormous dark, and every one of these ideas is someone standing at the edge of that light, squinting into the black, describing what they think they see. Maybe they're wrong. Maybe, somewhere in an unreachable bubble, another you is hearing the theory that turns out to be right. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.